Hello, good afternoon, everyone. Welcome back to our seminar series. So the topic for this year was mean curvature flow with surgery. Semester one, earlier in the year, we spent a lot of time talking about mean curvature flow, but we didn't actually ever get to the surgery. But fortunately, we've got an entire semester two in which to do that. So to start us along in this direction, I'm pleased to introduce to you Vishnu, who's going to talk to us about gradient estimates in mean curvature flow. Take it away, Vishnu.
Yeah, I'm not sure if we're quite ready to do surgery immediately because we just need to do one more main kind of estimate before we start like defining what a neck is and etc. But maybe since it's been a while since we've had our last seminar, I might remind us about the kind of two other things that the two other estimates we learned about from Tankai and Devesh. So we learned about the convexity estimates, which said that for all epsilon greater than 0, there is some constant C epsilon, which depends on initial data and the initial data, such that the smallest eigenvalue of the second fundamental form on your hypersurface xt is greater than or equal to minus epsilon times mean curvature minus this constant C epsilon. So, I mean, this estimate, what it basically says is the base goal of it is to show that if you take a blow-up sequence by the maximum mean curvature along a sequence in which mean curvature goes to infinity, then the resulting blow-up limit is actually convex. So that's what you can immediately kind of conclude from this. So maybe I should say one thing, that this C epsilon, as epsilon goes to 0, it goes to infinity. So maybe it kind of looks like it only applies to blow-up limits, but actually the convexity estimate is a bit stronger than it immediately appears. In fact, it says that even if you just look at the surface without blowing up, then the smallest eigenvalue won't go to minus infinity, right? But I don't know if there's an easy way to see why that's true just from the convexity estimate, but there is some maybe a bit non-trivial way to show that this implies that the surface doesn't have these exterior kind of pinches. Yeah. So yeah, convexity estimate, and then we also have learned about the cylindrical estimate. Which you can phrase kind of similarly, but I'm going to just use kind of this kind of formulation of it. So for all epsilon greater than 0, again, you have some constant C epsilon, which again depends on n and the initial data, such that a squared minus 1 on n minus 1 h squared is less than or equal to epsilon h squared plus C epsilon. So this isn't exactly the cylindrical estimate Tankai proved, but this thing on the right-hand side, that's what he bound to prove the cylindrical estimate. So, but we're just going to need this to prove the gradient estimate, this part here. So what cylindrical estimate, again, what it says is that if you take a blow-up sequence by maximum mean curvature along some sequence in which the mean curvature goes to infinity, then the resulting surface at that point we'll have all the principal curvatures except for the smallest one will be equal. So actually this thing, I just should have said that. So if you have a two convex, for two convex mean curvature flows. Okay, so I want to introduce kind of a space of, a so-called pinching condition, which is natural for doing mean curvature flow with surgery. Okay, definition. Actually, first, so what I want to prove in my few lectures is I would like to be able to cover the gradient estimate, and then using the gradient estimate, I want to prove the existence of these necks of certain kinds. I guess we'll have to define what a neck is. And yeah, so hopefully, I mean, maybe I will talk for we'll see if I can get those things done in 2 lectures, but otherwise I can do 3 lectures. Okay, so definition. So let X be an immersion of Smith manifold. Then we say that X is in this space CR alpha, where I'm writing alpha is some three constants, alpha 0, alpha 1, alpha 2, and R is greater than 0, and alpha 1, alpha 2, alpha 3 are all greater than 0 if it satisfies these following properties. So 1, lambda 1 plus lambda 2 is greater than or equal to alpha 0 times the mean curvature. 2, H is greater than or equal to alpha 1 R inverse. And 3, the area of M is less than or equal to alpha 2 R to the N. Okay, so this constant R is kind of like the scaling parameter for this family of for this space, right? So if I have X in C alpha, then scaling it by lambda X is in C lambda R alpha, right? So alpha is scale invariant for this. And to make alpha scale invariant, you introduce this parameter R. So now the reason that it's kind of useful for mean curvature flow of two convex surfaces is that if X is 2 convex, then you can choose R and alpha such that X is in some CR alpha. Then yeah, there exists R and alpha such that this is in CR alpha. Okay, so how do we choose these constants? Well, we basically just pick the ones that fit these conditions, right? So, okay, first of all, we can fix R, like we can usually when you have a scale, you can fix the scale. So I'm just going to choose R so that R inverse is greater than or equal to max M of A. And now using this, we can choose the alpha. Yep, so choose alpha 0. So alpha 0 here to be less than or equal to the min of M of lambda 1 plus lambda 2.
Vishnu, with your definition there, you've got alpha as alpha 0, alpha 1, alpha 2, but then you talk about alpha 1, alpha 2, alpha 3.
Try to do that? Where oh, whoops. Yeah. Alpha.
Normally I wouldn't worry about something, but I get the feeling that it's important which alphas are which here.
Yeah. Well, I guess I won't really refer to them that much, but it'll be useful later. Yeah.
Awesome.
But yeah, anyway, alpha 0 to choose that to be the minimum. Well, there are a lot of constants that come up in the next few chapters of the paper, so it's important to get on top of them early, I guess. Alpha 1 is less than or equal to, yeah, so of course, alpha 1, you want to choose it to be less than or equal to HR. And alpha 2, greater than or equal to R inverse mu, the area of M. And all of these things are things you can choose because, actually, maybe I should say, I did say that these are greater than 0. But of course, maybe this might not be, I said it might not be strictly 2 convex, but that's for the purposes of mean curvature flow, that's not actually a big problem because if you start off with a surface that is weakly 2 convex, then under mean curvature flow, it becomes immediately 2 convex. So you could make these greater than or equal to 0, but it doesn't really matter in this situation. Okay, so I mean, if you want to make a definition like this, you should hope that it is preserved under mean curvature flow. So let's check that. So if you start off in a space C alpha, then, oh wait, yeah. So if x0 is in CR alpha and xt is a solution to mean curvature flow, then xt is in CR alpha for all t, for as long as it exists. Well, I should say t in 0 t. Yeah. Okay, that's most of these conditions are pretty easy to check. Let's check them. So number 3 is, yeah, okay. So number 3 is probably the easiest. So you know the evolution equation for the area is equal to minus h squared times the area, t, depending on t, which is less than or equal to 0. So area is decreasing. So if area is decreasing, then clearly this is preserved for fixed alpha and Rn. Sorry, it should be r to the minus n here. The next one is condition 2. What was that one? Yeah, so I mean, we know the evolution equation for h, that's equal to h a squared, right? Yeah, and that's greater than or equal to 0. So lower bounds on h are also preserved. So the first two are done. So for the third one, number 3. Well, I actually don't know of a very simple way of arguing the third one. In the paper, there's like an argument that says that if you look at any, so, well, okay, let me just write it down. Okay, so if I have a lambda1 plus lambda2 minus alpha 0 h equals 0, so I can think of that kind of like the space of eigenvalues of a symmetric n by n matrix as Rn, I can think of it like that. And this condition here is a condition on Rn, right, for where the coordinates are the eigenvalues. So what I have here is I have a condition that describes kind of a cone in Rn. So if I look at the evolution of equation for Aij, that's equal to a squared Aij. So in the paper, this says that, well, it's on the cone. They want to use them. You want to use a tensor maximum principle. So on the cone, this thing is kind of tangent to the cone. So you expect that. So you know that if you're inside the cone, the positive side of this cone, you stay inside that positive side. But I wasn't too convinced by that. The only proof I know is that this thing here, this quantity here, if I write this as a function g, let's say I write g of x comma t is equal to lambda1 plus lambda2 minus alpha 0 h. Well, that's what that gives you is it gives you the distance. That gives you the distance from let me write this as g of some matrix, some symmetric matrix A, and I give it, and I define that to be this constant where h is the trace of A, and that gives me the distance from this point A in the space of n in Rn to the set where lambda1 plus lambda2 minus alpha 0 h equals 0. And then you can, I mean, you can kind of, this is not a smooth function, but you can show that this in the viscosity sense satisfies the equation G is greater than or equal to what is it? A squared G, from which you kind of get the same conclusion. But I don't know of a very easy kind of, I didn't quite understand in the paper the kind of one sentence answer to why this is preserved. But if someone knows that, they can interrupt me and explain exactly why that immediately implies this. Anyway, so yeah, so that's, I didn't quite prove the last statement there, but that's kind of like the summary of how this is done. Okay, so what do I want to do next? All right, so now we know that this family is preserved. Now what I want to do next is I want to phrase the cylindrical estimate here in terms of these spaces. Okay, so the quantities alpha, so this quantity CR alpha, that's a condition you impose on the initial surface when you're solving when you have a solution to mean curvature flow. So if I want to write this equation in terms of, in terms of these classes, what I really want is I want this constant here, which depends on n and m0. I want it to depend only on n, r and alpha, because r and alpha are kind of the things that you're prescribing. Is like information about the initial data. So hopefully it only depends on that, and we can actually prove that. Okay. So, Rob, let's say we have a solution xt to mean curvature flow with x0 in the class CR alpha. Then for all epsilon greater than 0, there exists constant C epsilon, which depends only on n alpha and epsilon, such that a squared minus 1 on n minus 1 h squared is less than or equal to epsilon h squared plus C epsilon r to the minus 2, right? So this is taking the role of that C epsilon before, and it only depends on alpha and n, of course, but like alpha is it only depends on that information about the initial data. Okay. So let's just start by setting r equals 1. Okay. So what does C epsilon in the cylindrical estimate above that we learned that Tankai proved? What exactly does C epsilon depend on? Yeah, you can kind of dig through the proof to kind of and follow the constants, and then you'll see that C epsilon, it depends on T, the initial volume, and some other stuff that depends on it. Yeah, is that it? Yeah. So if I want to prove that this C epsilon only depends on alpha, I want to check that T and the initial, the area only depends. I can control it in terms of alpha. Okay, well, firstly, I mean, I can control this by alpha. That's less than or equal to alpha 2, so that's okay. So now I need to control T by alpha. So T really depends. It was T, I think maybe earlier on in our seminar series, we learned that the maximal existence time is characterized by when the second fundamental form blows up. So we should be trying to bound the second fundamental form to kind of get a bound for T. Okay, so yeah. So we have this evolution for A. That's equal to 2a to the 4 minus 2 grad A squared. That's equal to 2a to the 4. Okay, so now we want to use the comparison principle to try and bound A. So we know that if we solve the ODE, phi dash is equal to 2 phi squared with phi of 0 equals 1. So wait a minute. Why do I want 5, 0 equals 1? Oh, sorry, I forgot to put a condition in my statement. So I'm fixing a scale R so that max A at the initial time when M0 is less than or equal to R inverse. Now, obviously that's not preserved because A can go to infinity, but I'm just saying that I'm choosing the scale R here so that max A M0 is less than or equal to R inverse. Okay, so that's why I need R. That's why I put a 1 here, right? Because initially my second fundamental form is less than or equal to 1. Okay, so if I solve this, I get 5t equals 1 on 1 minus 2t. So I know that I know that A is bounded for t greater than or equal to half. Sorry, t less than half. Less than or equal to half. So capital T is greater than or equal to half. So I need to get an upper bound as well. So this time I'll go partial t. I'll use the other equation, h, that's equal to ha squared, which is greater than or equal to 1 on n h cubed. It's kind of similar to this part here. We just use a similar argument and we use the fact, so h is controlled by alpha, right here. So using kind of similar reasoning to this ODE comparison principle, you get that t has to be less than or equal to n alpha 1 to minus 2. Okay, so t is controlled by alpha and n. Okay. Now that's for r equals 1. Yeah, so in this case, C epsilon is in this situation also controlled by n and alpha. So if x now in the general case, if x is in CR alpha, then R inverse x is in C1 alpha. So the previous statement is true for this. So I know that R to the minus 2, A squared, minus 1 on n minus 1. Oh, sorry, not R to the minus 2, R squared. R squared H squared, that's equal to epsilon H, R squared H squared, plus C epsilon, where this C epsilon only depends on n alpha. Because I just move the R squared to the other side and then that's it. So maybe I'll mention that you can do this exact same thing with the convexity estimate, and you get the same thing. C epsilon will depend on n and alpha, and you get it C epsilon R inverse here. Okay. Okay, so now I'll state the gradient estimate. Let's see how much time do I have left. Okay. So I have xt is MCF with the initial data in CR alpha. Then there exists two constants, C1, which depends on n, and C2, which depends on n and alpha, such that gradient of A squared is less than or equal to C1 A to the 4 plus C2 R to the minus 4. Yeah. Okay. So for T t greater than or equal to r squared on 4. Yeah, I think it's r squared on 4. In my notes, I forgot to write that down, but I think it's r squared on 4. So, okay. So the idea here is to bound this quantity. So grad A, okay, let me first write. So let's define G epsilon to be 1 on n minus 1 plus epsilon h squared minus a squared plus 2c epsilon r to minus 2. Right. So this is almost the same as this. If you move everything to the left-hand side in this quantity, right-hand side in this quantity, except I've added an extra c epsilon r to the minus 2 there. So this quantity also, yeah, so this constant c epsilon is the one that's given to you by the cylindrical estimate. That's greater than or equal to c epsilon r to the minus 2 because I have an extra copy of it. Okay, so the idea is to try and estimate nabla a squared divided by g epsilon g delta. Try to get something that looks like this, where this thing, where this thing depends on n only. And then what do we get? If that's true, then we get nabla a squared is less than or equal to cn g epsilon g delta. So then I can use Young's inequality to get cn g epsilon squared plus g delta squared. Yeah, so I'll bring the 2 out. Right? So maybe from this, can we get this thing here? Well, okay, so what we get, when we're squaring each one of these, we get terms of the form. So g epsilon squared has terms of the form a to the 4, which is good, comma h squared a squared, and it will also have terms like h squared, a squared, and a constant which is given by squaring that. Well, I'll just write it as c epsilon squared r to the minus 4. Yeah. So then we can get this inequality here from this, because we know that h squared is less than or equal to na squared. Okay, and so we this is what we need to do. Well, this is one thing. This does give you the answer. Oh, and also the c epsilon. Well, the thing is that in this inequality, you only have an n here. You don't have something that depends on the initial data. And the c epsilon squared, it depends on n and alpha, which is good because this term c2 depends on n and alpha, which is what we want. Okay, so if we can find a bound like this, then it's good. Maybe the question is, how do you find out what g epsilon g delta are, and why is an epsilon equal to delta? Well, I guess if you wanted to completely learn this and understand how this works, you would just write g epsilon g delta, keep it completely general, expand everything out, and try to figure out what epsilon and delta need to be. But that makes it more complicated. So for this seminar, I'll give some random numbers for epsilon and delta, which will give you the right answer, right? Okay. So before I fix values for these, let's compute the evolution for the quantity. Okay, I'll do that on a new page. Partial g minus partial g epsilon. Oh wait, yeah, let's just write down the other equations again. H squared. Okay, that's equal to 2h partial t minus Laplacian h minus 2 times this. That's 2h squared a squared minus 2 this. And of course, and we have this as well, which I think I wrote down earlier. And that's 2a to the 4 minus 2 derivative of a squared. Okay, so now we can calculate this evolution. That's 1 on n minus 1 plus epsilon. So maybe I can put with the same page. No, I can't. Yep, and then we get 2h squared a squared minus 2 derivative of h squared minus 2a to the 4 minus, plus 2 derivative of a squared. Okay, so now, so I'll just group all the derivative terms. So I get 1 on n minus 1 plus epsilon 2 derivative of h squared minus plus 2 derivative of a squared plus 2 plus 2 a squared 1 on n minus 1 plus epsilon h squared minus a squared. All right, so this kind of looks like G itself, except it's missing the constant term. So I'll just replace that with G epsilon plus the constant term. So, okay, then I'll just put this as 2. Minus 2, 1 on n minus 1 plus epsilon nabla h squared minus derivative a squared plus 2a squared g epsilon minus 2c epsilon r to the minus 2. Okay. And then, okay, so this thing here, so yeah, okay, so I can throw this out. Minus 2, and then I get that stuff again, the derivative parts, and then I get plus. Sorry. No, what do I want to do? So g epsilon minus 2c epsilon r squared so if I go up to this, g epsilon is greater than or equal to c epsilon r squared. Okay, so that should be a minus. Okay, so I should replace that with minus. That equals greater than or equal to minus 2a squared g epsilon. All right, so I don't really want a derivative of h here because the goal is I want derivatives of a, right? So I need an inequality that relates the derivative of a and the derivative of h. And so we have a nice inequality, a purely algebraic inequality, which says that derivative of a squared is greater than or equal to 3 on n plus 2 times derivative of h squared. Okay, so maybe I will just briefly sketch why this claim is true. So it's a nice trick where you write A as the sum of two orthogonal parts, E plus F. Okay, and you can write, so where E is the trace part of it and F is the trace-free part of it. So EIJK equals 1 on n plus 2 IHGJK plus KGHGIJ plus JHGIK. All right, so it's not really that difficult to show that E, comma F, sorry, the inner product of E and F, that's equal to inner product of E with minus E. It's not so hard to see that this thing is equal to 0. So if you take the inner product of E with A, then you get, since A is totally symmetric, it traces the A, so you get inner product of, you get all these terms, all you get is the derivative of H squared, right? And when you take the inner product of E with itself, you get the exact same thing. I mean, you get the same thing. So that gives you 0. And so you know that nabla A squared equals E squared plus F squared. Right? And E squared, you know, is this thing here. Look at E, you took it as norm. You just take the norm of each individual one. You have 3 copies of the same thing, so you get a 3 and the derivative of H. Okay. Okay, so we can replace this derivative of H with this by moving the, so you use this to remove the derivative of H. And so what do we get there? We get partial G minus Laplacian G epsilon is greater than or equal to 2 times so 1 minus n plus 2 on 3. So that's coming from the H, derivative of H. 1 on n plus 1 plus epsilon. And so this one term is coming from the derivative from just, oh, sorry, not H. So the 1 comes from this part, moving the minus inside, and then you get a n plus 2 on 3 coming from removing this derivative of H. Okay, and then you have the rest of the terms, which is minus 2a squared G, oh, sorry, G epsilon. Okay, so now I'm going to set what these epsilon delta is. So the two things, okay, so I'm going to define this constant k equals half 3 on n plus 2 minus 1 on n minus 1. So if this is greater than 0, if n is greater than or equal to 3, which is important. In fact, it's less than 0 if n is equal to 2, right? So that's kind of why this doesn't work if n is less, if n is 2. Well, yeah, and there's, you know, it doesn't make, it can't possibly work if n equals 2. So the two functions I'm going to consider are gk and g2k. Okay, so now, so the thing I'm estimating is going to be derivative of a squared divided by gk g2k. Okay, so if I set, if I look, let's first look at g2k. So partial t minus the Laplacian g2k, that's equal to so if I put 2k in epsilon, then this 1 on n minus 1 cancels. So I get 3 on n plus 2 times n plus 2 on 3. So I get a 1. So that just disappears. This whole term disappears. Okay, so actually I just get minus 2a squared g 2k. On the other hand, for gk, we still have that term, so you still have that gradient part. So partial t minus Laplacian gk. Okay. So that's greater than or equal to 2 times 1 minus n plus 2 on 3 times 1 on n minus 1 plus k, the derivative term, minus 2a squared gk. All right, so I'm just gonna compute this part here because I don't want to have to write this rest all the time. So okay, so 1 minus n plus 2 on 3, 1 on n minus 1, plus, now I have a half, 1 on, no, what's k again? Yeah, 3 on n plus 2, 3 on n plus 2, minus 1 on n minus 1. Okay, so let me just check, is that right? Yep, okay, so actually I'll just leave, I'll leave this as a k. I'll leave this as a k, there's no need to expand that. That's k. Okay, so I get 1 minus n plus 2 on 3 times 1 on n minus 1 minus n plus 2 on 3 times k. And if you calculate this thing here, then it turns out that this is equal to, it is, have I made a mistake? Oh, right, yes. Okay, so yeah, let's just write it as n plus 2 on 3, 3 on n plus 2 minus 1 on n minus 1 minus n plus 2 on 3 k, and this thing here is 2k. Yeah, it's 2k. Right, so you get n plus 2 on 3k. Right, so coming back to here, that's greater than, oh, that's actually equal to 2k n plus 2 on 3 a squared minus 2 a squared gk. Okay, so I mean, I may have to split up this proof over multiple, maybe just finish it off next week, but because there's a few more pages of calculation to do. But so what we need to calculate now, we want to calculate the evolution of this quantity here, right? Using what we've calculated so far. So maybe, you know, I always have to write these kinds of things down on a little whiteboard near my desk or on a piece of paper. Let's remind how you calculate the, you know, the heat operator on a quotient. So that gives me partial t minus Laplacian f h minus f partial t minus Laplacian h divided by h squared plus a gradient term. Okay, so we'll just apply this twice and then we'll have our evolution equation. Okay, for the first one, we have partial t minus Laplacian of nabla a squared on gk. We'll divide by gk first. So just to plug it into this formula, we get minus 2. Now the second derivative of a squared plus, oh wait, did I forget to say something? I didn't say what the derivative of I didn't remind everyone what the derivative of the derivative of a is. I mean the heat operator on the derivative of a is. Okay, so partial t minus Laplacian of this thing. So I can't remember if anyone actually covered this, but maybe if earlier on we proved long time existence, if a is bounded, then if we proved long time existence, we would have had to compute this evolution. So that gives us minus 2 Hessian of a squared plus some constant that depends on n, a squared, a squared. Okay. So this would have come up if we did if we wanted to bound higher derivatives of a in order to conclude kind of a smooth extension when a is bounded. Okay, so now we can do this. So partial t minus Laplacian of derivative of a divided by gk. That's less than or equal to, so this thing up here, 2 Hessian of a squared plus, I'll write it as Cn like this. Gk minus the next term, which is derivative of a squared divided by gk squared. And then you get this thing here. 2k n plus 2 on 3 derivative of a squared minus 2a g k. Okay, so this term can be simplified a bit more, and actually the derivative, oh wait, sorry, I'm missing a term. Yeah, no, I need the second derivative. I need the gradient term, gk. So we have all our main terms, which is this term here, this part, and this whole part here. But then we have some terms that depend on second derivatives here and here, right? So actually, we can combine this term and this term can kind of be combined in order to get a better equation. Okay, but first let me okay, let me decide if I want to stop. I might have to stop right in the middle of a calculation, which I don't really want to do. So maybe should I stop here or should I do half of this calculation and then stop?
Perhaps you could tell us where all this, are there key steps that you could mention and then explain in more detail next time?
Yeah, that might be a good idea. Okay, so yeah, I mean, this is not really a like an important thing, but this term here and this term here, they kind of combine to give you a much simplified. They kind of cancel out pretty much, right? So all these second derivative, higher derivative terms, they all cancel out, which is like the 7 lines might convince you of. And so what's the next step? So I mean, our goal is to next time compute this thing. Okay, and then what we'll get is we'll get something that looks like, let's call this thing f. We'll get something that looks like fa squared a constant, oh, I don't want to use K again. So it's a constant, I'll just say Cn minus F, something like that. We'll get some equation that looks like that. So if I look at a maximum, a local maximum of this equation here, then this thing is going to be greater than or equal to 0. All right. So if F is greater than this quantity here, if F is greater than this quantity, F is positive, like this quantity is positive. If F is greater than this, then this thing is negative. So we will get some kind of contradiction like that, right? So that means that nabla A squared on GK, G2K will be bounded by, well, F is that quantity, so bounded by Cn, something like that. Okay, and yeah, so I can finish that off next week, and then maybe we can start doing neck detect, use this gradient estimate to kind of prove the neck detection lemma. It's nice proof there. Maybe I should also mention that these 3 theorems that we learned, the cylindrical estimate, convexity estimate, as well as this gradient estimate, it's not enough just to do these, to prove these and then conclude that this works during surgery. What you need to do is you need to define, like, what we'll hopefully do is I don't know if we want to go through all these proofs all over again just in the presence of surgery, but when you define exactly what the surgery procedure is, then you need to verify that this inequality and this inequality are still true with the same constant C epsilon, with the same constant C epsilon and the same 2 constants here. I call them C1 and C2. Yeah, so it's basically you do this proof, and then there's like another non-trivial element which kind of intuitively should be true because you are cutting out a point and you're adding something that shouldn't decrease the convexity or how cylindrical it is. But that's a I'm not sure if we're going to skip that in this seminar series or if we'll just refer to the notes or something. So yeah, okay, I'll stop there.
Thanks very much, Vishnu, for a nice talk. Does anyone have any questions or anything similar that they'd like to discuss or ask Vishnu about?
That point you mentioned about the 2 convexity, the kappa 1 plus kappa 2 bigger than alpha H.
Yeah.
So it actually fits exactly into the vector bundle version of the maximum principle, which I'm not sure we ever did in the talks so far. But
that's what I thought, and I'm just wondering how, like in these older papers, how they maybe it was very obvious to them that this has to be true, but I don't know. They have usually all I see is like one sentence explaining why it's the case, and what they say is that you have this equation for A, drop the Laplacian term, and you get an ODE. The ODE preserves cones, therefore this quantity is preserved. It's not. I don't immediately understand that.
That's essentially what the vector bundle maximum principle says. It says if you have a subset of some tensor bundle which is say symmetric in some sense, or at least invariant under parallel transport, and it's convex in each fiber, and the ODE part in this sort of the reaction part of your reaction diffusion system for its evolution preserves that set, then the PDE does as well. That's really the statement.
Or at least like a point, like what you need is it points inwards, right?
At least not outwards. In this case, it points sort of tangent to the boundary, which is that's the idea.
Yes, I remember it being completely freaked out by the Hamilton's tensor maximum principle, because it is an ungodly statement. Well, it seems to me to be quite complicated, but I suppose I take comfort in the fact that it is quite intuitive, because I guess when I think of how PDEs actually work, you can use, essentially use the Baker-Campbell-Hausdorff formula. You say, well, what happens if you evolve a little bit by this term? What happens if you evolve a little bit by this term? And then you discretize it up and take limits. And if every single part of your PDE preserves a particular set, then you would expect it to be true when you throw them all together. This in part explains why convexity is so important, because you can easily cook up examples of solutions. If you imagine a function going from S1 to R2, a circle is not particularly convex. Somehow you shouldn't expect, because of how the heat equation works, you shouldn't expect anything to work without convexity. But I don't know if that's helpful, but this is how I think about such things.
Yeah, that's roughly it. So this part about being tangent to the boundary exactly handles the zero order terms in the evolution equation, and the convexity handles the diffusion terms, the Laplacian, which otherwise could possibly push you out of the set. So once you met the combination of the two assumptions is just enough to give you a maximum principle. Yeah, that's right.
Why does the cone? It turns out that the cone also needs to not just be convex, but to something a bit stronger, contain the positive cone, for example. So not all convex subsets of the positive cone seem to be preserved necessarily.
But it doesn't contain. Oh no, it contains the positive cone.
Well, it needs to be So the trouble is you have two notions of convexity. One is convex as a function of the eigenvalues, and the other would be convex as a function of the tensor in each fiber, and they're different things. If it happens to be that you have this relation to the positive cone, then they agree, but it's not always the case.
Yeah, very good.
Yes, you could probably have an entire semester dedicated to explaining the tensor maximum principle, perhaps, but
there are at least 3 proofs that I'm aware of.
Are they all correct?
I believe.
All right, good. Any further comments or questions for Vishnu? All right, great. Then let's. Oh, sorry, you had another comment, Ben?
No, just say thanks, Vishnu.
Yeah, thanks again, Vishnu. Let's thank the speaker again.
Thanks.
All right, we'll come back to you with details later on when the next talk is going to be. And also, I'd just like to remind you that we're still looking for speakers. I expect that this semester will be a bit more laid back in terms of frequency of talks, but nevertheless, it would still be good to have people volunteer to take on a speaking role if such a thing becomes important, if we turn out to need another speaker. So just keep that in mind. I think it's a good opportunity for PhD students in particular to really, well, I'm sure Vishnu can attest to the fact that he was really forced to understand some of the more complicated and technical parts of this paper. And on the other hand, we also like seeing PhD students talk. All right, I'll stop speaking. I'll stop the recording there. Thanks all again.